Hello and welcome to the 5.2 notes. And this is a very, very important section over our study of integration, and it kind of puts into play why we are using integrals. So the first thing that I want to do is I want to take a look at a situation where we are driving a car at a velocity of 60 miles an hour. Okay, so this is a velocity graph, and we want to calculate the total distance that we travel over 1 hour. We want to use the formula that distance is equal to the rate at which we travel times the time. Okay, so the thing that I want to show you guys here is that the rate at which we are traveling. Okay, the rate at which we are traveling is equal to 60 miles per hour, okay? And the time at which we're trying to determine this is over a period of 1 hour, okay? And so if we take distance, okay, the total distance that we're traveling, then that's going to equal the rate, which is 60 miles per hour times 1 hour, okay? And so what we end up getting here is we get a total distance of 60 miles, okay? So, that's something that we've been doing for a while. You've seen it in science class. You've probably seen it in a math class before this. But we need to figure something out here, okay? What I want to show you is that we're taking a rate and then we're multiplying it by a time, okay? But I want to show you something. I want to show you that using this graph, we can figure that same thing out using this graph. Now, what I notice here is that if we take our rate at which we travel, that's our y-axis here, okay? Our y-axis is a rate measured in miles per hour. So I'm going to come over here and label this as a rate. And then I know that my x-axis is a measure of time in hours. Okay, so I'm going to come over here and I'm going to measure that this is measurement in time. So now let's think about it for a second. Okay, we took a rate and multiplied it by time. Now, if I think graphically about this, I'm really just taking one length and multiplying it by another width. And so if I were to come here and draw a line at 1 and say that if I took, using the graph, this length r times this length t, then that gives me the area under this curve, okay? And so this is our area, okay? All this area, okay, and I'm going to put an arrow. The area under this curve is equal to our distance, okay, for this example, okay? Now, what I want to talk about here is that, we can find the area under this graph, okay, pretty easily. It's not very hard for us to do this math, but I want to use some notation here, okay, some special notation. So this is really important that we write this down, and this is our special notation. Okay, and we're going to use the integral symbol, okay? And I'll explain to you later on why this works, but I want to show you that the area, okay, the area here, the area under the curve, okay, we'll use the word curve even though it's a straight line, is going to equal this. Okay, the area is going to equal the integral between 0 and 1 of 60 dt. Okay, and so, this notation here, folks, is what we would use to show that we are calculating the area from 0 to 1 underneath the constant graph of 60, okay? And that's all it is. And And the area under the curve can be represented by this integral, okay? This is an exact measurement. Exact measurement. Okay. And I want you guys to see that this area here, this measurement here, is equal to 60 miles. Okay. And so I'm going to use this notation, start to use this notation of what this means. But I want to go through with you a couple of other scenarios and how we would actually calculate the total distance traveled of a car traveling at a certain speed. Okay, so let's take a look at something else. Okay, it's pretty easy for us to calculate the area when we travel at a constant speed. Okay, using our formula, distance is equal to rate times time. But let's think about something else. Let's think about a car that is slowing down. Okay, and let's say that the car is traveling at a decreasing constant speed. So over the course of 10 seconds, okay, we were traveling at a rate of 50 feet per second, and over the course of 10 seconds, we come to a stop, okay? But we are slowing down at a constant speed, or at a constant rate, okay? So what we want to do is we want to calculate the area under the curve, okay? And I'm going to call this function here just v of t, okay? Just to make it easy on ourselves. And what we want to do is we want to calculate the total distance, okay, that we travel over 10 seconds. So what I want to do is that our distance, okay, I just want to write this real quick, is equal to the integral from 0 to 10 of our velocity function v of t dt, okay? That's what our distance is. Now let's think about why we get that distance, all right? And all I'm going to do is calculate the area under this curve, okay? And I know that this is a triangle, all right? So I know that my my area, okay, of this object, or of this graph is going to be 1/2, okay, times the base, which is 10 seconds, okay, and then I'm going to multiply that by the height, which is 50 feet, and I'm going to do this per second, okay, because when I multiply it by this rate, and if I use this notation of a 50 feet per second, okay, what I can show here is that my seconds divide out, and my measurement is left in feet, okay? So quickly what I want to do here is just do the math, and we'll get area is equal to 1/2 times 10 times 50, okay, so area is equal to 5 times 50, and so area here is equal to 250, and this is a measure of feet, okay? And this is our total distance, okay? This is our distance traveled, okay? Distance traveled, okay? So if we want to express, this distance in terms of using some calculus notation, then we would use this, okay? And we could say that the distance that we travel, given this scenario, is equal to 250 feet, okay? So we can actually, it's a really powerful thing that we're actually doing here. But the other thing that I want to show you is that, in these two examples, guys, we're dealing with some fairly straightforward concepts, okay? Traveling at a constant rate of 60 miles an hour, we can easily calculate the area under the curve using geometry, okay? Same thing here. We can calculate the area under this curve using geometry, but we want to consider something else, okay? because the real world doesn't really always work in these simple terms. And so let's apply this to a new concept, okay, something else, all right? So let's think about changing decreasing velocity, okay, where we still go from 50 feet per second, but we might be slowing down at a very, very much faster rate to come to a complete stop, okay? This is something more typical that you would see if you were driving a car coming to a complete stop. And so the question is that, you know, it's the same thing applies, okay? Our distance, okay, is still going to be the integral between 0 and 10, and I'll call this function v of t, of v of t dt. Okay, that's our distance, okay? And this is going to be an exact distance, okay? But we've got a problem, okay? And the problem is that we don't have any sort of method currently that allows us to approximate the area, or to calculate the area under the curve, okay? However, what we could do is we can approximate this, okay? So first of all, let's write this, that there's no geometric method to calculate the area under the curve. Okay, there will be, just not right now, okay? So we have no way of doing this geometrically, but what I want to show you guys is that instead, we can approximate it. We can approximate the area by using rectangles, okay? And so we'll be able to find the exact, you know, area or the exact distance that we're traveling, okay? But currently we don't have a way to do that. But what we can do is we can approximate the area by using rectangles, and that's what we're going to do in this section. And so what I would do is something like this, okay? You know, if I made a series of rectangles here, okay, then what we could do is we could calculate and get a reasonable area under this curve and take the area of this rectangle, take the area of that rectangle, take the area of that rectangle, the area of this, the area of that, and the area of this. Okay, and the area of those rectangles will give us an approximation. So what we want to do, okay, our goal is to calculate the area of the rectangles to approximate the total distance traveled. Okay. So this is just, you know, guys, the big idea of what we're doing here. This is very, very conceptual, okay? There's not much in the way of mathematics right now as far as what we're doing on this first page, but I want you to understand, you know, what we're trying to do here, that the area under the curve is equal to the distance traveled, okay? And so, you know, I'm going to go ahead and stop this video, and we're going to do another one here in a little bit. But let's go ahead and tune into the next one. Thanks. Bye.